So thank you very much for having me, and thank you for pronouncing my first name actually perfectly. This talk is over C, or field of characteristic 0, and so it's a joint work with Fabio Bernasconi, Stefano Filippazzi, Nikolaos Tsakanikas, and there's also an appendix written by Niklas Müller, who already mentioned the work. So let me tell you first a little bit of background history. So the story is that there's quite a lot known or has became known in the past 10 years or 15 years in the KLT case. So let's assume that we have a projective KLT pair, and so if you don't like KLT varieties, then you can also assume just that you're dealing with a smooth. So X is smooth variety, and delta, the support of delta is normal crossing, simple normal crossing. And then KLT just means that the coefficients are between 0 and strictly 1. Okay, so you can think about this case if you don't want to think about the singular case. And I guess this is already interesting, because then log-canonical just means that you're allowing coefficient 1. Okay, so in this setting, there's been quite a few works in the past 10-15 years about the Beauville-Bogomolov decomposition, and so let me mention just the summary of some of them. So first, in the Kx trivial case, let's say numerically trivial, but it's equivalent to Q trivial. So yeah, Q delta is a Q divisor for me. If there's like MMP people in the audience, so Kx plus delta, so not a real divisor. So Kx plus delta is trivial. Then the statement that there is a quasi-fine quasi-étal cover. So quasi-étal means that that it's étal in codimension 1. Such that, let's say this is gamma, the cover. So if you look at y and the pullback, the divisorial pullback of delta to y, so you pull back along the regular locus, and using that it contains codimension 1, you just extend divisorially. So this is isomorphic, this splits, right? So it splits as 4 different things. So so first there's a rationally connected factor. Really the boundary makes it rationally connected. Then there's an abelian factor. I don't know if it's visible, this kind of size of letters, so let me know if not. Then there's a lot of symplectic factors. I don't know, maybe y. So these are the symplectic factors. And there's a lot of, or there's possibly a lot of, there can be a lot of strict Calabi-Yau factors. So let me not define what these precisely are. Of course, in the singular case, it's mildly trickier to define them than in the smooth case, but it's similar. Abelian, of course, it's not singular, but the other factors can be singular. And also we can see that the boundary somehow is concentrated on the rationally connected part, which is, I guess, not overly surprising if it's... So really there's like one question remaining in this business, at least in the KLT case, as far as I understand. It's this that the fundamental groups of the symplectic and the Calabi-Yau factors are trivial, but maybe you will tell me that it's known in one of the cases. I'm not that sure about what the situation with this is. But in any case, why am I mentioning that? Because yes. So these are singular. Yeah, that's why there's the fundamental group question, because of course this is well known in the smooth case. But so the reason I'm mentioning, because then if you, this is also simply connected because it's rationally connected. So you see that there's really the fundamental group is at least conjecturally concentrated in the abelian factor. So this conjecture implies that the universal cover is the rationally connected part cross C to some power, right? That's the fundamental times the rest. Okay, so I'm writing up this form because this is what kind of generalizes well to the next case that I would like to present. So the next case would be what happens if instead of kx trivial, you look at minus kx nef. So let's see what happens then. So, attribution. I forgot to write it, so let me say it in words. So it's a cumulation of many people's work. So I guess Quebecus, Greb, Péternel, Guenancia, Höring, Drual, Campana, Chao, Matsumura, Wang. I guess this is hopefully for the singular version. And then there's the smooth version, which was shown by Beauville and Bogomolov in the many years ago. Okay, so what happens in the kx nef case? So now let's assume that we have no boundary and x is smooth, and minus kx is nef. So in this case, it was Höring and Chao who proved that so in this case somehow, and I make an example on this, you cannot expect the finite splitting, like splitting after a finite cover. So only thing you can expect is this thing that was following up by the conjecture, that the universal cover splits, and luckily they were able to show this. So if you take the universal cover of X, then it's isomorphic to factors as there. So formally, actually, there's no difference. Maybe the only thing I forgot to write there, which is obvious from the situation, is that there the canonical of f delta f, like the log canonical, is trivial. Now if you drop that and you allow yourself a minus kf, so a Fano here, then you get to their result. Okay, so this is great. So why it doesn't work with a finite cover? So does not work. The example is quite easy actually, but I'd like to maybe with a finite cover. So the example is simply the following. You take X to be the projectivization of OE plus L. So E here is an elliptic curve. And what's important that L is degree 0 but not torsion. So in this case, so you can see that if you take a finite pullback, then L will not become trivial, and then this cannot be trivialized. So what is this geometrically? This surface? It's a ruled surface, right? Over an elliptic curve. And so definitely it does not split after a finite cover. Why is it minus kx nef? Maybe just a little. So actually, if you take the two sections just given by the two projections to the two factors, then you can easily show by a junction that kx plus d is actually linearly trivial. And then that means that minus kx is linearly equivalent to d. And then it's clear that it's nef, right? Because the self-intersection of both sections are actually just the degrees of these, and both have degree 0. So it's clear that this thing is nef. Okay, so indeed the theorem does not work with I wonder what else I would like to say. Not that much more. Somehow I wrote more things here on my notes, but I'm not sure why. Yeah. So it does not work. And yeah, I know what I want to say. So why it doesn't work? So why cannot you take here just a finite cover to have the splitting? So the real reason is that if you think about it, here the fundamental group it also comes from just the base, and the point is that that if you trivialize this, so let's say you go to the I wrote this to the bad spot. So if you go to the universal cover, which is just given by just pull back to the universal cover of the base. So this is the universal cover. Then the point is that there's a monodromy action on the automorphisms of the fiber, because it's an isotrivial family, so you can see that it's even locally a trivial family, so you can see that there's a monodromy, and so it acts on the automorphisms, on the log automorphisms of the fibers, the monodromy. And the point is that this monodromy the image of the monodromy has infinite order. Okay, so generally you shouldn't expect any kind of finite cover, like splitting on a finite cover, whenever you're involving things with infinite automorphism. Okay, that's the message. So maybe I write this out. So if you have automorphism is infinite, then no finite cover. All right. So that's what was known about the kx minus kx nef case, and then one would be tempted. So definitely. So my understanding that the KLT case is not known for the minus kx nef case, but nevertheless there's this theorem known by so this was, I think, originally shown by this generality by Kodonyi, Zidanovic, and myself, that even though the full singular Beauville-Bogomolov decomposition is not known in the minus kx nef case, you can still show this consequence, or I'm not sure it's really a formal consequence, but it's definitely related. What Niklas was already mentioning, that so back to the KLT general case, at least the Alban isomorphism is known to be a fiber bundle. So it's locally analytically trivial. All right. So these are kind of the known results, and then one could wonder what could be if there's a log-canonical version. So I think this is a supernatural question. Actually, whenever there were all these KLT results coming out, I was always asking people, like, okay, what of log-canonical? And actually people thought, yeah, sure, but this is a good question, like the authors of those articles, but somehow, like, there were no results. They said, like, the methods were not working. So in any case, based on the results above, what could be a natural setup? And let's focus now on the k-trivial case. So, sorry?
Just one more question regarding your theorem 3.
Yes.
I mean, can you maybe go a bit further and like split up the Calabi-Yau and the symplectic factors so that you're just...
So what I understand is that this is maybe not known. I'm not sure. Wait, if I mean, you can go a bit further. Like, there's a similar theorem, I think, possibly with some hypothesis for the MRC fibration. So that might give you something you want. Okay, so the question was, can you split up the Calabi-Yau and the symplectic factor at least? So yeah. So maybe that other theorem would give you something like that. Okay, good. So what's the key here? That if so we had a finite cover statement in the KLT case, but what I argue is that that's not possible in the log-canonical case already from the start, and simply because the automorphism group doesn't have to be finite. So in the KX trivial case, it's finite, but as soon as you go log-canonical, it's not. So the best thing one can hope for is yes? Oh, you think so? Okay, maybe it works. So sorry if it works? Okay. Okay, good. So it works for any KLT pair, that one too. So yeah, we can discuss after the talk, because this is like literature. So I'm not 100% sure exactly what's known and not known. But anyways, so the only natural question based on the above discussion for the log-canonical case is that so we have a pair which is KX trivial and log-canonical. So the only natural question would be if the universal cover, and actually here you shouldn't really take universal cover, but the universal quasi-étal cover, which is the normalization of the universal cover of the regular locus. So you could, so let's call this y, and then the only natural question would be if y may be split as something rationally connected cross affine cross symplectics cross Calabi-Yaus. Okay? So I hope I persuaded you. This is because, again, the finite cover thing does not work because of the presence of infinite automorphisms. Yes?
How do you normalize this universal cover of X type? Because in general you need finiteness to complete. So now you're in a non-compact setting. You need the finiteness.
Are you sure you cannot normalize?
No?
I think you should be able to do it still. No? You think this is an issue?
I'm a bit worried, but
okay.
We can discuss after.
Okay, we can discuss. But anyways, whatever is the statement, it's not true. So, but we can. That's why I went not completely. We can. No, but it's not true because of other reasons, right? So, I believe this should still exist because you would have the same singular. No, you. Okay, I have to say I'm not prepared to argue here. But good question. But so anyways, whatever this normalization is, and I really hope it exists, then the answer is no. There cannot be such a decomposition. And the reason is this other theorem. So this is the actual theorem I would like to talk about. So this is our theorem. So ours is that if you have a, so for each D at least 4, there is a projective log-canonical variety X such that of dimension D, such that first Kx is trivial, second the Albanese is an elliptic curve, so the Albanese variety. Third, every fiber is birational to only finitely many others. So every fiber of the Albanese birational to only finitely many others. And third or fourth is that the fundamental group of the Albanese is actually isomorphic to the fundamental group of the regular locus. So anyways, whether this normalization exists or not, if it exists, so let's say the conjecture involves even the existence, but this example shows that no, you cannot have this kind of decomposition on this hypothetical universal or quasi-universal cover. Yes? Because we don't have examples for lower dimensions. And it might be true actually in lower dimensions. Okay, this we didn't try to prove, but I wouldn't be surprised. Actually, it's a good question. Okay, so I mean, it's definitely true in really low dimensions. So yeah, like dimensions for surfaces, I think it's true. Just for stupid reasons, like, yeah, it's log-canonical, just a single point, right? Like for surfaces, somehow it's, and for 3/4, you might wonder. I'm not sure what the answer is for 3/4. Okay. Anyways, so this is our theorem, and I write up this other theorem, but not because this is hard to show. So this is much easier to show than the construction. So the construction is not horribly hard to prove. Still, it takes like 4 or 5 pages to work out the details, but it wasn't easy really to get to find it, at least for us. So this other theorem is much easier, and we didn't have problems. What is it? That you pass to the, if this quasi-tal universal cover would exist, it would be given by passing to the, by just base changing to the universal cover of E. And there you would have a fibration so that the fibers are not birational to each other. And that to a Stein. And that would mean like it's okay. You have to think about it for 3 minutes, but that would mean you cannot split. Okay, so good. So theorem B is the reason I'm mentioning. So it's much easier to prove and to come up with a proof, at least with the current technology. But it tells you kind of what the counterexample should look like. Yes?
So you use three which have only finitely, but they are not completely isomorphic, right? otherwise, I mean, we don't get a counterexample.
So there's only finitely many other fibers to which every fiber is isomorphic. So you have, okay, you have E, you have X, and you know, if you pick a fiber, there's only finitely many others to which it's birational, okay? Not just isomorphic, even birational. And so it means that if you pass to the universal cover, if this universal cover exists, it would be given by this, and you can see, because this is Stein, you would need to really split this map, and that map cannot be split because.
Can you explain to the all rationally connected fibers? Is that where you're going?
It will be, but you don't need that. You don't need that to show that it's not splitting, right? I think it follows just from this. But it is, they are rationally connected. Okay, so what's the positive statement which shows you how the counterexample should go? So you take a log-canonical pair with minus kx delta. So what you can show is what Niklas mentioned already, is that the Albanese is locally stable. So all the fibers are semi-log-canonical. So this you can show with the canonical bundle formula, which will, I mean, you can also do it differently. Like, there's many ways you can show this, but eventually they all boil down deeply to the same Hodge theory statements. And you can also show that every, and this is important for us, that every LC center, so actually this follows from the locally stable. No, it actually does, no, yes, it follows. So this is a, so every LC center dominates the Albanese. And so what is an LC center? Let me recall. So it's an image of a divisor with discrepancy -1, okay? So these are somehow special subvarieties when you do MMP. They are very important. And so they have to be horizontal over the Albanese. And even more, if you take the smallest one, and if you normalize it, sorry, this goes up. So if this is the normalization of the smallest one, of a minimal one, so minimal log-canonical center, then the map to the Albanese is actually still birationally isotrivial. So there is some kind of isotriviality always in the picture. It's just not the big thing. Okay, and so we will return to this when we construct the example. But maybe let me also put up a theorem C, which is unrelated, but somehow it's also a counterexample, so something similar. So you could ask, instead of this fiber bundle statement, just surjectivity. And that's even known in positive characteristic. This is I proved with Shoegiri in 22. And so when I gave lectures about it, then every birational geometer, oh, but maybe the singularity assumption is not even needed. Maybe it's just true for just the minus kx assumption, the surjectivity of the Albanese, and the statement is no, that's not true. So there is a normal projective threefold And then you can, of course, go up to higher dimensions by just taking product x with minus kx nef, minus kx ample, actually. Sorry. Q Cartier. But of course, the singularities are worse than log-canonical, because otherwise, you see, it's a locally stable, so it's surjective in particular, such that the Albanese is not surjective. Okay, probably I will not be able to say anything on this, but it's also a fun construction. We had a lot of joy doing it. So, all right. So, let's go then to the actual counterexample. I guess the rest of the talk will be just about that. Okay, sorry. I'm just still learning these boards. There's one more here. So, you see, like, maybe I can use this picture here. So what? Okay. No, maybe I'll start the actual counterexample. So the counterexample. So let's assume you have this counterexample. So assume x is given. Then you can always take this so-called DLT blow-up, where you extract all the discrepancy -1 things, and if your guy had rational singularities, then the Albanese doesn't change, and in our example, actually, that's true. So you can, so if singularities are rational, we can assume that that actually can replace x by the DLT model. We can replace x by x delta DLT. So might look like making things worse because now you're introducing a boundary, but these are much easier to deal with, these gadgets, because this is basically what it is. It's simple normal crossing plus KLT instead of just log-canonical. So somehow this is a very vague statement for what it is. It's even misleading to some point, but still kind of shows you that somehow the non-log KLT behavior is somehow concentrated in some part which works like a simple normal crossing. So it's much easier to deal with. So that's why. So our tactic that we're going to construct this one, and then we just contract the coefficient 1 part of the boundary, which will be all the boundary, and then we get to our example. So okay, so we construct something which is almost simple normal crossing, but with boundary. All right. So how is the construction going? So it's a construction based on pencils, and so it's really it uses this. So it's really a Fano construction, and what's difficult about it, I think, whenever you do some kind of Fano construction, is just to fit in the world of Fanos, because Fanos are bounded. You have very little room to do whatever you want to do, and actually, like we tried a lot of pencils, and it was somehow never working. We couldn't get. I mean, it's always over P1, right? A pencil, And then we had to base change in the end to an elliptic curve. And for that, we would need to have the relative canonical divisor trivial of the pencil. But for that, the actual canonical divisor has to be the pullback of O minus 2. And somehow it's really easy to write down examples where it's O minus 1. But get to the minus 2, it just was not working. And then in this specific construction, somehow magically, it turned out that I still don't understand, like, if there's any theoretical reason behind it, that one component of a fiber is contained in the boundary. So we could contract the other component, and then that meant that a whole fiber was in the boundary. So you could just throw away that, and then the log-canonical divisor became the pullback of O minus 2 instead of O minus 1, and then, okay, we won. So that's roughly speaking I guess the idea behind the whole construction, and also the other thing I can say as a takeaway kind of message is that the canonical bundle formula is very useful to control the singularities of all fibers. Usually we can control very well the singularities of the general fiber, right? Usually it's just the same thing as the singularity of the total space. But the canonical bundle formula is this magical weapon which we can control how many singular fibers you have and what singularities. So okay, so this is the maybe the two takeaway message I can say. So what's the actual construction? So we start with a simple pencil. And so it's a pencil in, let's say, PD. And it's, so I write out the actual equation because it's important. So y0, y1 are the coordinates of the base, and x0, xd are the coordinates of PD, and the equation is the following. And it's actually really important, the actual form. So we take a general equation. So this is just general degree d homogeneous polynomial. Okay, so nothing surprising. And we add to it yd times a general degree d minus 1. Sorry? X. Thank you. And general okay. And so what's the idea here? Maybe I write down the other part also, but it's just a pencil of two things which look like this. And so this is also general Q1. And the idea is quite simple. So if you look at, if you restrict anywhere, you will see that that all fibers contain the vanishing locus of f and xd. And so xd just defines a linear subspace and of a PD minus 1. And so you can have a degree d hypersurface in there. So this is a Calabi-Yau, so a smooth Calabi-Yau, okay? By a junction. Like, okay. So these are degree D, so the smallest index Fano hypersurfaces that contain a fixed Calabi-Yau of lower dimension, okay? And one lower dimension, and it's just a general such pencil. Let me know if there's any questions about that. And what is the boundary? So the boundary is just the vanish, is just the hyperplane section. So in particular, for a general fiber, it cuts out exactly this S, okay? And there's a special one for which it cuts out more. Okay, what are the important things to notice here? So, okay, so this is the construction, and then the rest of the talk will be just a lot of properties of this construction and maybe what kind of MMP you do with it. So, okay, first note, so there's a dimension count which tells you that like these two things, like if you restrict to y0 equals 0 and y1 equals 0, these are not projectively equivalent. And this is just a dimension count. So I write down the actual. So first thing to note is that, again, you restrict to the y0 equals, or the y1 equals 0. So then you get just f plus xd q0. And you restrict to the other one also. So these are not projectively equivalent. Because just a dimension count again. And I can, this is so fun, so I cannot stop writing it. So the reason is this. Okay, so that's it. Good. So what does that mean? So that means that you see, like if you look at the smooth part of this pencil, so let's call it, I don't know, U. So this is the smooth locus of pi. Oh, I shouldn't have touched it with my own hands. Sorry if I broke the system. Should have used the buttons. Sorry. So if you look at the smooth locus of y, then you have actually a map. So these are known to be k-stable. So this family you just restrict to U. Then you have a moduli map for the corresponding k-stable moduli space. And you see that there's 2 points that go to different points. Two points of U that go to different points of the moduli space. So this is generically finite. So in particular, it follows that only two, so to any fiber, there's only finitely many others that are isomorphic to it. And to get to the birational statement, you just have to use that the degree D hypersurfaces in PD are birationally superrigid, okay? Plus degree D hypersurfaces are birationally superrigid. I mean, we reference this statement from Kähler's article or book. I'm not sure what the origin is. Okay, so we see that actually the we see that actually the birational, the non-birationality of the fibers is done by with this construction. But of course, there's a lot of other things to worry about. So let's talk about the other parts. So so then, yeah, let's compute the canonical bundle of the pencil. So it's just given by equations. So the canonical bundle is super easy to compute. Just use a junction. So you take the canonical bundle of PD cross P1, which is O minus D plus minus 1, O minus 2. And then you just add to it the degree of X and the degree of D. So, so if you do all these things, then you get minus D minus 1 minus 2 plus D1 plus 1, 0. So let me write this up. So the second note is that if you compute the canonical bundle formula, I'm talking about that, then it's O minus D minus 1, comma minus 2. So this is for PD plus or tensor. I mean, I'm mixing the divisorial and the sheaf notation, which is a horrible thing to do, but let's go with it. So this is for X. And then there's O10 for D. Okay, and so you get to O0 minus 1. Okay, with other words, it's the pullback of O minus 1 from the base. Okay, and as I said, you really have to get to minus 2 to be able to pull back to an elliptic curve to get 0. So so really, that's one thing to verify. The other thing to verify, it's not clear at all that this has log-canonical singularities a priori. So the general fiber is smooth, that's clear. But what about the special fibers, right? So that's where the canonical bundle formula comes into picture. To controlling the singularities of this pencil. I mean, not of just X, but of the pair. For X, it would be easy to control the singularities because you just blow up the intersection, whatever. But you want to control it for the... And yeah, you want to understand actually not just of the total space, but the singularities of the fibers, because you want to do manipulations with this family. So, okay, so maybe I can start here. So, so how many singular fibers? Yeah, I guess that's right. So how many singular fibers, or how many maybe I just write singularities of the fibers. All right, so what's the key here? Of course, I prepared a longer discussion on this, which I don't have time for. So I have to finish when? At 55? Wow. So you have the canonical bundle formula. Okay, so then this will be very short, this discussion. The magical canonical bundle formula, where you know that this is actually an F in this case because you're working over a curve. Otherwise, it's just pseudo-effective. And the point is that singularities of this guy is the same as the singularities of that guy. So if this is log canonical, if and only if that is log canonical. And even more, this thing detects whether you are whether the fiber. So it has coefficient greater than 1 at those points over which the fibers are not log canonical or not semi-log canonical, or over which the total space is not log canonical, sorry. And so by just counting degrees, you can see that that actually the total space is log canonical. So everything is okay in that respect. Essentially because this is like 1, -1, -2, and you see that this can be at most 1, the degree of B. And then the key is to realize that actually there's a single singular fiber, and that singular fiber has two components. One that I would call T, and the other is a PD -1. And this singular fiber, the divisor, the boundary divisor, contains this thing. So the boundary divisor goes through the intersection, and it contains the entire half of this singular fiber. And so what you can do, you can contract T by running some adequate MMP, and then you can subtract this whole fiber from the boundary. And then you get to a case where instead of -1, you have -2 here, and then you can pull back to an elliptic curve, and you are happy. So this is how you get the DLT counterexample. But then there's still a boundary. If you get a boundary-free example, you still want to contract this. And that we do, as you well know for surfaces. So when you have a k-trivial surface and you have something in the boundary, a coefficient 1 thing, then you can always blow up that by staying crapant. And if you blow it up enough times, then after a while the self-intersection becomes negative and you can contract it. So we do the same thing here. So we blow up a positive enough divisor in the boundary, and it stays crapant, the pair, and then we can contract it, and that's it. So, okay, I guess I stop here. Sorry if the final part was...
Are there any questions or comments?
Any questions? One where you ask for the computation for the log-canonical case.
For log-canonical case, and so in the components of the compositions, do you require any singularities for strictly Calabi-Yau varieties or holomorphic symplectic varieties?
So I guess in my question I was just asking for log-canonical singularities, right? Or I'm not sure I understand the question.
I mean, so the singularity is restrictions on the component of the decompositions. Do you have any restrictions on that?
I mean, our theorem says that there's this decomposition doesn't exist. So I'm not sure what to say. What would be the good singularity requirements for the factors, because the factors then don't exist either. Like, not as part of the decomposition. I mean, they exist as a standalone object. You can still study log-canonical symplectic varieties as log-canonical Calabi-Yaus, but whatever you do with them, however, it will not be motivated by a decomposition statement. So you can choose your own restrictions, basically. This decomposition will not tell you any interesting somehow restrictions, okay, because it doesn't exist. Ah. So we contract the other one, no? because we want to remove this from the boundary to decrease the canonical bundle. Sorry? Yeah, it gets contracted T exactly. And maybe it's worth pointing out that T is, sorry, it's a D minus one, so it's a D minus 1 degree hypersurface. So you can think about it like a cone over, yes, well, I'm not sure it's 1 point. Is it contracted to 1 point? I mean, it's a divisorial contraction, so MMP doesn't give you a priori, like statements whether it's contracted to a point or to something of positive dimension. Yeah, I cannot say this, but definitely I think as an approximation, you can think about it as a cone over a D minus 1, but I'm not sure if it's actually contracted to a single point.
Isn't the T also just given by a hypersurface?
Yeah, so it's a degree D minus 1 hypersurface. Yeah, so it has to be contracted to a point. Okay, you're right, yes. So you will get here a singularity which is, I mean, without the boundary, it's still KLT, but it's quite close to being not KLT.
Your restriction on the dimension, does it only occur in this inequality that you wrote on this board, or anywhere else?
So I think with this birational superrigidity, you also have a problem, because one dimension lower, you have cubic surfaces. So there. So definitely you cannot do it 1 dimension lower, because you would do it with cubic surfaces, and there all cubic surfaces are birational. So you cannot have this. You don't have this. There's no moduli for cubic surfaces. So yeah, I don't know what happens for 3/4. I agree. One should sit down. Probably it's something doable, like maybe it's a good PhD thesis question or something like that.
Okay, so let's thank Zsolt again.
Thank you.